All right. Hello, everyone. We are teams of Khalifa Tower, and first I would like to introduce my team members, Grace, Shiheng, Evan, and also Jennifer, currently in US, and myself, Tony. And today, we would like to give you guys a presentation regarding with the self-house structure interaction on fundamental period of the Khalifa Tower. So first, I would like to introduce Grace to give us a brief overview and motivation of our project.
So the presentation will be divided into seven parts: the motivation, objectives, background, methodology, result and discussion, summary and conclusion, and statement of contribution. So I will be covering the motivation and objectives part, and Jennifer will be covering the background, and Shiheng will cover the methodology part, and Tony will cover the result and discussion, and while Ivan will cover summary and conclusion and also the statement of contribution. So firstly, why do we choose to undertake this project? This is because firstly, when the four choices appears in the poll, we found Khalifa Tower to be very captivating because it is the tallest building in the world in Dubai, and it has 163 stories. But then we begin to wonder, although Dubai is not in a seismic zone, it is located near to a very active seismic zone, which is in Iran. So we begin to wonder, what if Dubai gets influenced by the seismic activity, and how should this tallest building withstand the earthquake impact? And according to the municipality of Dubai, every building in Dubai is built according to withstand the earthquake impact. And the Burj Khalifa itself is built to withstand the impact of a magnitude of 7 of an earthquake. And we choose to focus mainly on the part of the soil pile structure interaction, because through hearing to professors lecture and also doing some research by ourselves, we found that soil pile structure interaction has an impact on the fundamental natural period of a building. So what is the fundamental natural period or the natural frequency of a building? So basically, fundamental natural period is an intrinsic value of a building, a construction. Like this material is hard is an intrinsic value of this material. The fundamental natural period is an intrinsic value of this construction. So during the earthquake, there are many different sinusoidal waves that have different frequency, and one of the frequency will inevitably match with the natural frequency of this building. And when this occurs, resonance may happen. When resonance happens, it means that the trough and peak of the frequency of the building and also the frequency of the earthquake matches, and thus the amplitude will superimpose on each other and thus create some detrimental impact on the building. And this will result maybe in the collapsing of the building, like in the one instance in the Roman history when the soldiers' stepping frequency matches with the bridge frequency and causes the collapse of the bridge. So it is important for us to figure out the natural frequency of a building, and thus helps us to predict what is the maximum deformation of the building when the frequency of the earthquake matches with the frequency of the building. We will do this by employing a comparison between a building without pile and another building with the pile, because we want to investigate how does the soil pile structure interaction influence the natural frequency of this building. And we will perform two analyses. The first one is the modal analysis. Through modal analysis, we can find the natural frequency of this building, and through harmonic motion analysis, we will be able to impose some different a force that has different frequency ranging from 0.1 to 1, and thus we can see how does what is the maximum deformation of the building when the frequency of the force that we impose matches with the frequency of this building. The objective of our research is to investigate the influence of soil-power interaction on the natural frequency of the structure. And next, I will invite Jennifer to give us a brief introduction of our project.
Thank you for the nice introduction. I'm going to go ahead and talk about some of the background history of the Burj Khalifa, as well as some information about its foundational build. So the Burj Khalifa could be said to have been a recent project as it was built on January 4th of 2010. It's located in Dubai, and it not only stands tall at 500,000 tons as a symbol of the UAE, also known as the United Arab Emirates, but is also a physical representation of the country's foresights and wants. The three talented architects on the screen who had designed this marvelous 162-floor building was intending to go for a neo-futurism architectural style, which was essentially incorporating urban design that connects with human values, as well as displaying the usage of technology, for which you can tell from its modern interior and the aesthetic exterior shell. Next slide, please. So when talking about the inspiration of the Burj Khalifa, we have to talk about the spider lily, which is a regional desert flower. So this particular flower is widely cultivated in the lands of Dubai, and aside from the three-leaf structure, similar to how the petals of the flower protrude the stem, as you can see in the pictures, the side wings of the Burj Khalifa also extends from its central core structure, showing their many shared characteristics. Next slide, please. So when talking about the usage of the building, there's a variety of purpose that was destined for this tower, but its original idea was to make it the tallest skyscraper in the world. It has now been incorporated into a residential hotel, restaurant, and home to a lot of entertainment that attracts tourists from all over the world. The meaning of the tall height of the building holds more than just aesthetics. It was meant to symbolize the fast progression of Dubai and acts like an emblem of the Middle East. When it was first built in 2010, the Burj Khalifa was the tallest building in the world, and this was also done so to signify Dubai's role and position, more specifically to emphasize the necessary existence of Dubai's oil trade through tourism. Next slide, please. So let's take a look into the interior foundation, and I'm going to give a brief summary. The foundation of this building is supported by large concrete raft design consisting of 3.7 meter thick foundation and an underground pile supporting system. This particular design allows the weight of the building to be spread across a large volume, decreasing specific weight load at any point. The tower's unique Y-shaped structure provides both aesthetic and shapes the core of the building. Its functionality also reduces wind force and setbacks, provided by its stable configuration. The Y-shape is also addressed as a buttress core, which is a structural system with three wings extending from its core and heavily reinforced by support systems. And this type of structure will allow each individual floor plate to provide a different width. The shaping of the building will cut down wind flow, which is especially needed in tall buildings for emphasized safety and durability. I would now like to welcome my teammate Shi-Hun to talk about the methodology of the model structure.
Okay, thank you, Jennifer. And now I'm going to introduce the methodology of our group. So our methodology are mainly about two aspects, the geometric model and structure properties in analysis. You can see that in our model, there are two parts. The first part is main building, which is the tower as shown in the right picture, and the second is pile foundation. The third is soil stratum. These are three pictures of our main building. You can see the connection between main building, pile foundation, and also soil stratum from the side view. And about the top view, do you guys still remember the inspiration of Burj Khalifa? That is spider lily. And our top view of model exactly looks like a blooming flower. Our main building was constructed tier by tier, and every subsequent tier will be narrowed than the last tier. For the first three tiers, the wings in all three directions will be set back, so that the shape of first three tiers are kind of similar. However, since tier 4, there will be only one of three wings be set back. You can see as the sketch shown right here, the right bottom corner of the sketch is set back and other wings are intact. After this sketch being extruded, there will be a new tier with one wing being set back, constructed. And in general, our model is in a spiraling shape. And the next part is pi foundation. Our initial pi foundation refers to the foundation plan, official foundation plan, and there are 192 pies on it. Each pie is about 47.25 meters long. However, this initial pi foundation just too complicated, and the number of meshes on it exceeded the numerical limitation of ANSYS. So we have to simplify our pi foundation. We reduced the number of piles from 192 to 15, as shown here. To make the influence of this modification on efficiency of foundation as little as we can, the total cross-section area of simplified foundation and initial foundation are same. And the length of it is also unchanged. Besides, the location of simplified pies are also well designed after calculation. And next is about soil stratum. There are 4 layers in our soil stratum, and there is a blank space among the middle of soil stratum that is preserved to the pi foundation to prevent overlapping of model in advanced analysis. And the second part of methodology is structure properties. And I'm going to talk about the materials that we assign on our model. For the main building and pi foundation, the upper structure of main building is structural steel, and lower part is tower concrete. The foundation just default concrete. The difference in density of this concrete as shown here, and the density of main building is calculated by using the total weight of Burj Khalifa, which is 500,000 tons, divided by the volume calculated by ANSYS. And Young's modulus that we applied here are just from engineering data of the ANSYS. And then is material assigned on our soil strata. There are 4 layers. The first layer is made of soil, and the second layer consists of limestone. The third layer is about sandstone, and the last layer also limestone. Of course, our soil strata was simplified, but to guarantee the accuracy of our Young's modulus, the Young's modulus of every tiers here are obtained by weighted calculation of thickness and Young's modulus of submaterials inside every layer. And then is connection method that we use. For the contact regions between upper structure and the lower structure of main building, and also the pi foundation is bounded to simulate the real condition. And for the contact regions between pi foundation and every layer of soil strata, that's frictional. And the frictional coefficient is about 0.3. And the last thing I want to mention is mesh. Our meshes model is generated automatically by ANSYS, and with default mesh size which equals to 87 meters. And as I have mentioned, the number of meshes in our initial pi foundation just 2 in normals. And after simplification, you can see the mesh on our simplified pies just much more simple, which fulfills the restriction of academic version ANSYS. And that's all for my part. And now let me to invite Tony to give us introduction of modal and harmonic motion analysis.
Thank you, Shiheng. In order to verify the natural frequency of the mean tower and investigate the influence of soil power interaction, our teams have conducted both a model and harmonic motion analysis of the structure. Also to have a better understanding of the soil power interaction, we have sketched the structure, two type of structure that like shows on the slides. On the left hand side, the structure is without power foundation, and on the right hand side, the structure is included a power foundation system. Here's the result of our model analysis, and this structure is do not contain a power foundation system, and as you can see, the deflected shape, and for mode number 1 and mode number 2, and here is another model analysis result that the structure with a power foundation system, mode number 1 and mode number 2. Okay, so at the end of analysis, we come out 2 tables that contains the natural frequency of the structure under the mode 1 to mode number 6, and the left-hand side, the table shows on left-hand side is the structure that without the power foundation, and also the table shows on right-hand side is the structure with the power foundation system. And the result indicates that the structure with a power foundation system would have a large natural frequency, but a small natural frequency, but a large fundamental period. This indicates that the slow power interaction may increase the fundamental period of building. So we have also do actual harmonic motion analysis to simulate the seismic motion and verify the natural frequency of the building. And as you can see on the slides, here's the deflection shape of the building that without a power foundation. And when looking at the period equal to 13 seconds, the structure has a maximum response amplitude equal to around 50 meters. I would say that was pretty makes sense because the period, the fundamental period of building was approximately equal to 30 seconds, and also harmonic motion, the period of harmonic motion was equal to 13 seconds. Therefore, in this situation, the renaissance occur. So the structure would have would act in a maximum response. And here is another deflection shape that the structure that includes the power foundation system. And when looking at the periods equal to 23 seconds, it has the structure has a maximum response amplitude equal to 17 meters, and that was also makes sense because the fundamental period of the structure that have a power foundation was approximately equal to 17 seconds, and that's the value is approached to the period of the harmonic motion. So, and in this situation, the renaissance occur. So the structure have the maximum response. Oh, also, I would like to show you guys the total deformation for the on the top of the tower is equal to 3 meters that have a power foundation, but it's 4 meters do not have power foundation. Therefore, the 1.5 power foundation has less deflection. So overall, our model analysis is successful, and our teams have achieved our analysis goals. So, but they're still necessary to review some of the field assumptions and modeling decisions. So our project focuses entirely on modeling and sketching the external building features. But our teams do believe that the interior structural components may or will significantly impact the fundamental period of building. So we have computed the mass density of the building by using the total mass of the structure divided by the total volume of the structure. The second point is the soil layer property and soil stress parameter included in ANSYS may not be the same compared to the exact set half. Some soil layer properties and soil stress parameter, including friction angle, engine shear stress, are not considered in ANSYS software. but we only input the modulus of elasticity of each soil layer into the ANSYS. The second point is the power group composition configuration is complex. In reality, the Khalifa Tower was constructed based on 200 piles in a power group, but we just because ANSYS cannot be able to solve a multiple mesh and to give a solution, so we just simplify and adjust the piles to a small, large diameter piles and less pile in the power group. Although the hierarchical motion analysis of our structure generates meaningful results, but there are some limitations restrict us to investigate the soil power interaction under a seismic loading. So the point is the ANSYS cannot mobilize a seismic motion because earthquake is not considered as a hierarchical motion, and the seismic analysis required hazard response spectra and peak ground acceleration to calculate the phase shear and lateral displacement of the building. And also, this topic may relate to the set effect and wave propagation. So, and this topic is way complicated than we expected, and we have not included in analysis part. But please know that we have some of the seismic historical events mentioned in literature review section. So that's all about the discussion and analysis, and I would like to introduce Evan to give us a brief summary and reflection of our project.
Oh, okay. Thank you, Tony. Let me briefly summarize the presentation of our group. So what our group basically did is that we conduct a harmonic motion analysis to verify the natural frequency of the tower. And the result manifests that, oh, sorry about that. And the result manifests that with SPSI, which means that soil power structure interaction, will decrease the natural frequency and increase the natural period of the tower. So it also means that with SPSI, the piles are really helpful of resisting vibrations caused by earthquake and increase the stability of the tower. So let me repeat the result of our group again. So the natural frequency of the tower without pile is 0.072 hertz, and the amplitude of the wave is 50 meter. And the natural frequency of the tower with pile is 0.043 hertz, and the amplitude of the wave is 13 meter. Okay, so our model does have some limitations, and I summarize it here. So first, we lack soil material and modeling, which means that it is not realistic to simulate the real soil state in ANSYS. For instance, we use soil, limestone, and sandstone in our foundation model. However, a wide variety of materials are utilized in the real foundation base. For example, sand, kalk tufa, sandstone, conglomerate, siltstone, and mudstone, according to the research done by Jandy and Jandy in 2004. And second, the materials are said to be linear in ANSYS, which plots against pressure and deformation, which means that if you add the pressure onto the material, the deformation will certainly increase in linear. But in real, the materials are not all linear, so it will cause systematic errors and then cause influence to the natural frequency and natural period. And third, our model doesn't 100% match the real shape and structure with the real Khalifa tower. So the weight and volume of the model is not 100% the same with the real tower. So according to research done by Murty in 2004, mass is correlated with the natural frequency of the tower, so our results may be affected because of the mass and the volume. And for the fifth limitation, in reality, the structure is partially void. But in ANSYS, the structure is set, the default is set to be solid. So our group realized this issue, so we changed the mass density role to maximum match with the real mass density of the tower. But this change will definitely cause a problem in cause error and uncertainty in natural frequency. But it matches with the first and second mode according to the analysis. And for the last limitation, the number of casting place pile is not exactly the same compared to the real number of casting place pile. So according to what Shihan just introduced, that we, in order to simplify our model, we just constructed 15 casting place piles. But in reality, there are more than 150 piles. So the difference in number of casting place piles will certainly cause the uncertainty and error in natural frequency and natural periods. In addition, our computer cannot match and calculate the results. So for improvements, I think that if we can get access to ANSYS 4 edition, we can get better results regarding with natural frequency and natural periods. And also for further studies, I think our topic will be determining how pile configuration influences the anti-systematic performance of the Burj Khalifa tower. Tony? Oh, wait, sorry. Let me briefly introduce our contribution to you guys. So Tony works on results and discussion, modeling, and paper compiling. And Shihan mainly works on methodology and modeling. Grace works on literature review, methodology, and paper editing. So I work on reflection, statements of author contributions, conclusion, and PPT editing. And Jennifer works on introduction and executive summary.
Thank you, Evan. So our modeling and analysis process is very successful and help the team to further understand the relationship between the solar power interaction and the fundamental period of building. And we would like to thank for our Professor Burha to the support and help on both sketching and analyzing the structure. And also we would have thanks for our teaching assistant Blair and Curtis for help and support. Also for all of the classmates. Thank you all.
Very
beautiful. To give any comment or question.
Beautiful slides. Thank you all for a wonderful presentation. Just one remark. I think Tony said that they replaced the number of piles with 15, but made sure that the cross sections are the same. Is that what you said, Tony?
There's a question for you from Professor Burha. Tony is just wearing his earphone just now.
Just one short note, because I know that you need to catch the dining hall, or you will run out of food.
Can you say it again, Professor?
Yes, didn't you say that you replaced the piles with 15 piles as opposed to